All right, so let's do some calculations with standard enthalpy of formation and then standard entropy values to calculate the change in enthalpy of a reaction and then the change in entropy of a reaction, and also together with those two, we can calculate the standard change in Gibbs energy for that reaction, which ultimately we can use to calculate the equilibrium constant or the reaction extent for that reaction. So let's start with this reaction over here. We will calculate the delta H first, and then delta S, and so forth. Okay, so now when we calculate delta H reaction from this given data, let's see if I have the correct. Okay. What we need to know is to calculate delta H reaction. Right. Let me see. There you go. Okay. Delta H reaction is the sum of standard formation enthalpies for the product minus the sum of standard formation enthalpies for the reactants. So P is for products and R is for reactants. So products minus reactants. Okay. Now what we want to do is we are given the products, which is over here, and then we have the reactants as well. We'll add the enthalpies up. That's what we're going to do. Okay. Now we have, for the products, we have formation of 1 mole of NH2Cl. Not formation, let's say that we have 1 mole of NH2Cl in the balanced chemical reaction. So the delta H reaction should be 1 mole times the standard formation enthalpy for NH2Cl, which is minus 85.6 kilojoules per mole. And then to that, we need to add the formation enthalpy for H2O, which is H2O liquid, which is, we have 1 mole of that, 1 mole times minus 285.8 kilojoules per mole. So let's do this. Let's calculate the formation enthalpies of products and reactants separately. Okay. And if you do this, moles cancel out, you're going to end up with a value which has units of kilojoules, and then that value is, let's see, minus 85.6 plus minus 285.8, and that is minus 371.4. 371.4 kilojoules. Then we're going to do the same thing for the reactants, the sum of formation enthalpies for the reactants. Okay, so we have 1 mole of NH3, 1 mole times NH3, formation enthalpy is minus 80.8 kilojoules per mole, plus for HOCl is minus 26.2. And we have only 1 mole of that in the balanced chemical reaction. So 1 mole times minus 26.2 kilojoules per mole, and moles cancel out. And to add these up, you're gonna get 100, 106, 106 107 exactly, right? Minus 107 kilojoules. Okay. Now we have these guys. So what we're going to do is we define the delta H reaction by taking the difference, products minus reactants. So delta H reaction must be minus 371.4 kilojoules minus 107.0 kilojoules. Okay, and if you do this calculation, you are going to get minus, no, let's do this. Okay, minus 107. $264.4 minus 264.4. Right, so I think, and that is closest to option B in our answers. Okay, so we have that value, delta H value, to be minus, let me write this down separately, minus 264.4 joules. Okay, now let's do the same thing with delta S. I'll do it here and then we'll look for the answer later. Okay, let me see. All right, let's get rid of some of these. I'll leave delta H reaction here so that we can refer to it later. So delta S reaction is the same thing, products minus reactants. So to do that, let's first get the sum of standard entropy values for products, which is going to be a product side in is 2Cl, which is, we have 1 mole of NH2Cl, which has an standard entropy of 97.7 joules per mole per Kelvin, plus we have 1 mole of water, and then that is going to be 109.6 joules per mole per Kelvin, and moles cancel out. You're going to get an answer in joules per Kelvin, and let's see, and that should be, let's say 199.6, 206.6 should be 207.3. Okay, we'll check our calculations a little bit. Okay, and then we're going to do the same thing for reactants. Okay, so we have 1 mole of NH3. So NH3 has a molar entropy of 111.3 joules per mole per Kelvin. To that we need to add 1 mole of molar entropy of HOCl, which is 36. Right, nice round number there. Mole per Kelvin. Again, moles cancel out. You're going to get an answer in joules per Kelvin. So 111 plus 36 is 147. 147.3. 147.3 joules per Kelvin, And then to calculate the calculate the change in entropy for the reaction, that should be products minus reactants, should be 207.3 joules per Kelvin minus 147.3 joules per Kelvin. Okay, and this seems to be 207.3 minus 147.3. Wow, it seems to be 60 joules per Kelvin. Okay, so we have a delta H of minus or negative 264, and delta S of positive 60, which is going to be a delta H is negative, delta S is positive. That means this is going to be productive at all temperatures. So anyway, so that's based on the sign of delta H and delta S. Okay, which is great. And now what we can do is we can use this to calculate the delta G for this reaction, the change in standard Gibbs free energy at, let's see the temperature. The question, I think, is 100 degrees Celsius, at 100 degrees Celsius. Okay, now let's do that using a different pen. All right, let's do delta G. So delta G reaction is delta H reaction minus T delta S. Okay, so we have everything. T is 100 plus 273 to make it Kelvin. So let's plug in chunk. Delta H is minus 264.4 kilojoules minus temperature 100 degrees Celsius is 373 Kelvin, and delta S is 0.06 kilojoules per Kelvin. Okay, and now obviously this is going to be a negative value, and then all right, I'm going to need need a calculator to do this. Actually, 264.4 kilojoules minus 373 times 0.06. Yeah, let me do that. 373 times 0.06. Or remember, I got 0.06 by dividing 60 by 1000 because I wanted to convert joules to kilojoules. And I get 22.38. 22.38. Okay, and then this is almost like 22.4. So if you add it's kilojoules again, and if you do this math, and it turns out you're gonna get 286.8, close to 286.8. Yeah, a little bit less than that, but anyway, let's say 8 kilojoules negative. Okay, minus or negative value of 286.8 kilojoules for delta G. Okay, now the next thing we can do with this is I wish I had more space here. So let's remember this value. The delta G was minus 286.8, minus 286.8 kilojoules. Okay, now with that, what I want to do is, let's see. Okay, so we did that. Delta H was 264, minus 264, and delta S was 60 joules per Kelvin. Not, that should be per moles, that's incorrect. and then delta G was 286. Okay, let's go. And then all right, so what we're gonna do is at 100 degrees Celsius, I want to calculate the K value. Okay, so this is not relevant to this, but anyway, we'll do it. Okay, calculating the K value because we know delta G now. Our delta, no, let me use a different pen. Okay, so our delta G reaction is minus 286 kilojoules. Okay, now what we're going to do is we know delta G naught reaction is minus RT natural log of K, and therefore natural log of K is minus delta G over RT, and then K is so we take to get the K value from natural log, we need to raise to the power of E. So we get K on the left hand side and E to the power of minus delta G reaction over RT on the other side. Okay, now let's plug and chug our values. So here the R is 8.314 joules per mole per Kelvin, and then temperature, I think our temperature was 100 degrees from previous question. We can stick with that. So that is 373 Kelvin. Okay, so if we plug and chug the values, delta G is minus, okay, we negative 286 times 10 to the power of 3 joules. Okay, I converted kilojoules to joules because my gas constant R is in joules, and then divide this by 8.314 joules per mole Kelvin times 373 Kelvin. Okay, let's say this is per 1 mole, let's say. Right, and these are my numbers now. I have all my numbers. Now what I need to do is I need to plug and chug these numbers into a calculator. I need to do this with a calculator. Okay, so let's do that. I have minus 286 times 1000 divided by 8.314 times 373 Kelvin. All right, and if you do that, you're gonna, I got minus 92.22. Okay, so with the numbers I got e to the power of minus sign is here, minus 92.22. 92.22. Okay, so these are not no units now, units cancelled out. Okay, now this is great. Okay, in other words, our K value must be at 100 degrees e to the power of 92.22, because minus times minus is positive. And let's see, I'm going to get a redonkulous number here. Exponential 92. Oh yeah, 92.22 is a huge number. I know. Anyway, 1.1 times 10 to the power of was 0. That's what I got. Okay, we should all check that as my K value. So I just did this calculation because it's not because it is on top hat. I just want to show you guys how to use that value and calculate the numbers. So we have to be careful when you plug these numbers in the calculator, because unless we have our parentheses correctly, we can make a mistake very easily here. So we have to be careful there. Okay, and that is that. And then let's do the question on the screen. Actually, use the data to determine the temperature range where the following reaction is product favored. Now, here's the thing: this reaction has a delta H, the negative delta H. Okay, that means products are favored by the potential energy, and also it has a positive delta S, meaning products are favored by entropy as well. So if that is the case, it's going to be always product favored. So it's going to be option C. So there's no calculation here for that. Okay. Now I think that's it. That's all. I mean, we can do with this data. I mean, you can be given a table of delta book values of delta H formation and standard entropy values, and with that we should be able to calculate delta H reaction and delta S reaction, and with that we can calculate the delta G reaction, and once we have the delta G reaction we can calculate the K. So that's it. All right, I hope this helped. I'll see you guys in class. Bye everybody.